Hello, hello. No, the board is still coming. Hello, hello. The board is waking up. Hello, hello. I'm waking up. No, I'm not. Good afternoon, Natalie. All right. Good afternoon, Janice. Are we going in? Hold on. Good afternoon, Kaya. Good afternoon, Yanel. Good afternoon, Kaya for the double. Good afternoon, Yaneli for the double. Good afternoon, Natalie for the early. Good afternoon, Genesis. Good afternoon, Chastity. Good afternoon, Carlos. Good afternoon, Mariam. Good afternoon, Brian. Okay, did that work? Okay. Um, and thank you for your patience. As I keep saying, and I don't really harp on, the exams are just coming really slowly. Like some of you have them back, some of you don't. They're just coming and coming, and 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 we're all just catching up. Well, I'm catching up. Hold on, I'm setting up the. So I apologize again if you have gotten your exam and you have any issues with it, text or email me. And at the very least, even if you can't come to my office hour, we'll talk on the phone or something. Or again, if you haven't got one back and it's really starting to make you edgy, which I understand, then also text or email me. We'll talk about it either way. Hold on, but they're just going to keep coming until they stop. Um, Hold on, I'm just getting the board going. Okay. Okay, okay. Hello, Annie. Hello, and hello, who's that? Oh, that's me. Okay. 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 Oh, wait, there may be something in the Oh, good afternoon. That's quite a okay. Yes, good afternoon to you. Okay. So um it's that time again. It's that time of the semester where, well, I certainly am just still trying to catch up. I always fall apart after the middle of the semester. Maybe some of you do too, or I apologize to those of you who don't. But what that means on your side is everything we're talking about right now. The last homework that will have ever been assigned is homework 7. We're going to keep talking today about concepts that are in homework 7. Then we still have things to do after today, but there's no new homework on them. You'll see. Um, Hold on. Regardless of the due dates or whatever, especially because I'm taking so long, of course, you guys can still turn in homework 7 or old homeworks. You should. If they're old, you might not get full credit, but you'll get enough credit to be worth it. If you are trying to catch up as I am, or you're playing catch up and you're trying to do old things to get points now, I totally respect that. Um, just I would urge you to go in backwards order. Like if you're trying to turn old things in, go from the most recent in order from to the least recent. I may have mentioned this before, because then you'll understand better what's going on in class. And also, like the older something is or the farther back it is, I'm not going to give it as many points as something that's somewhat current. So go in backwards order if you're trying to catch up. Also, please know, since I'm catching up or not catching up, that anything that you've done, like particularly all the game participation and stuff. I haven't been sending back points in a while, and I'm aware of that. But they're there. You're getting credit for them. They are going to be tallied up and count. Please know that. I have to catch up, but they aren't disappearing. I promise you that. And the later I take or the longer I take with things, the more generous I am with them. So um I just hope that's all clear. So we're all just doing that. Oh, you fell apart. Okay. All right. So but now what I want to talk, but I'm like interested in the physics right now. So the physics of Gauss's law, which is what homework 7 is about, right? We did a couple of big examples of how to apply Gauss's law last week. They were a couple of big examples from homework 7. I'm going to do a couple more examples now. Also from homework 7, I'm not necessarily going in the order of it, or, I'm not reading it out verbatim. I'm just doing the stuff that it is asking you to do, so that you can make sense of it. And then, but then whatever I get through today is what I get through. And then the next few classes, I'm going to say other stuff that's all coming from this conceptually, but that's past the level of the homework questions and that you won't do any new homework on, just so you're clear on this. So there's nothing new for you to do. Just keep catching up whatever you're doing. I'm just choosing it. Oh, wait, why is it not? Sorry. Okay. Oh, sorry. Okay, so here we are. Here we are today. Okay. Um, the first law on the page that you see right here. Good afternoon. Thank you. Good afternoon. I still owe you, direct chat person. I know. I'm aware, and I apologize. Um, the first equation, the first statement on the board right here is Gauss's law. I definitely want. We're spending a lot of time on Gauss's law because it's very big. It's very important. It is like the electrostatic equivalent of Newton's second law. I mean, it's like the center of everything even if it seems, well, whatever it seems like it is. Um, the top law on the page is Gauss's law. That's what we're dealing with now. Now, the law underneath it is what I want to get to from there. But we may not get there today, and we won't actually. So the second law you don't necessarily recognize yet. It's the goal of where this discussion is heading, so that you know. But um, where how I want to start that discussion is to continue with cases of applying Gauss's law, electrostatic law, to cases from the homework number 7. So specifically, everything we've done so far in homework 7, everything we've done so far to practice applying Gauss's law has been in the case of points and spheres, right? Like last week, well, specifically spheres. We talked about conductors versus insulators, and then you were asked to consider 4 different cases. Uh, uh, when I say consider 4 different cases, or when I say consider a case of Gauss's law, or when I say use Gauss's law to solve, let me quickly remind you what I always mean by that is you have a bunch of charge in some kind of shape over here, a continuous distribution of charge in some kind of shape over here, and you're being asked to compute the electrostatic field over here. That's always like the point these days. And when I say you have a shape of charge, when I say you have a continuous distribution of charge, I mean like a shape. Like last week, the shapes were spheres. Today, they're going to be shaped more like cylinders, the shape of the charge themselves. When I say you're trying to figure out the field over here, I mean as a function of displacement from like the center of that shape. That's always the issue, is there's a bunch of charge super close together so that's like smooth and it's in some kind of shape. We want to know what kind of field does that shape of charge produce in the space nearby it. So, and the whole idea is that we use Gauss's law to compute the field. Again, just to remind you or to bring you up to speed, Gauss's law, this top law on the board, it's a law about flux. It makes a statement about electrostatic flux. It says that the flux through any closed surface is always fully determined by the charge enclosed by that surface. The law is making a statement about field lines through a surface, but we use the law in order to compute the field line at excuse me, to compute the field itself, the field function at a point in space. So flux is about through a surface. Field is about at a point. We still care. We still are ultimately trying to figure out what is the field at any given point in space due to stuff that's happening in space. But the trick, the technique is to invoke, is to consider closed surfaces, because Gauss's law tells us something that's sort of always true and always reliable and always sort of simplifying about all the field lines through a closed surface. So we use our knowledge of closed surfaces as a middle agent in order to get to the ultimate punchline of field. That's what like we're always doing now, and that's what we did last week. So we had the homework asked you to do four spherical cases: a conducting sphere outside to figure out the field outside a net charged conducting sphere, to figure out the field somewhere inside the net charged conducting sphere, and then to figure out the field outside a net charged insulating sphere, and somewhere inside the insulating sphere. I'll tell you right now, I'm not going to write it down because I'm going to rabbit hole. I'm going to tell you right now the answers for those four cases. Like we did some in class, but we didn't do all. We just discussed. And here's the answers for those. For the conducting sphere, anywhere inside the conducting sphere, what you get, no matter how methodical or careful you are, you get that the field everywhere inside the conducting sphere is zero, assuming it's a stable conducting sphere, assuming it's a conducting sphere that's been sitting there for some time, which the homework does say that it is. You get that the field anywhere inside the conducting sphere is zero because the field anywhere inside any kind of conducting body, stable conducting body, is always zero. That's like what we discussed in English last week. But if you go through the procedures and you do Gauss's law, you can mathematically confirm or expand on that English, and you find that the answer to case A, or whatever, case one, the field anywhere inside a conducting sphere is zero. The field anywhere outside a conducting sphere, if you do the problem, we didn't do this together, but if you do it the exact same way that we did the field anywhere outside the insulator, the field anywhere outside a conducting sphere turns out to be this. Well, you do the procedure the same way that you try to compute the field anywhere outside an insulating sphere. You do the Gaussian procedure, which I'm going to repeat today in a different example, but you have it in your notes from last week. If you do the Gaussian procedure the same way for outside an insulating sphere or outside a conducting sphere, you find the same result either way. Because as it turns out, if you're outside the sphere, all the math, all of the physics and all the math is exactly the same. The field lines are the same. The Gaussian surface that you use as a Gaussian sphere is the same. The charge enclosed is the same. Either way, whether you're outside a conducting sphere or you're outside an insulating sphere, the field function that you get is E equals 1 over 4 pi epsilon naught Q over R squared R hat, i.e. Now I'm saying this all, I know it's all very abstract if you've never thought about it before, but hopefully you've thought about it with me last week. What I'm saying is the answer that you get in the homework for the field outside an insulating ball or outside a conducting ball is the exact same field function that you get if you're outside a point, which is just that original Coulomb's law result. Constant times Q over R squared is the magnitude. What I'm trying to say, now that's if you're outside, whether it's a conductor or insulating sphere, or it's a point, they're all the same result. Because what I'm trying to emphasize here, what I want you to see before I move on to the other cases, what I want you to see is that I think I wrote, no, I didn't write. Wait, did I? Hold on. No, I didn't. Okay. What I want you to see is that all of those cases, point, copper sphere, glass sphere, they all have what I would call zero-dimensional asymmetry. A point and a sphere are similar in that they're both asymmetric with respect to no axes of space. There is not one axis of space that a point or a sphere picks out and treats as somehow special or different. That's bizarrely important, as it turns out. Like, that's the nature. Like, round things are like dots in that respect. More physically or more concretely, I'm saying the field lines from a dot are the same. The field line diagram from a dot is the same as the field line diagram from a ball, which is that the field lines radiate out the same way in the same fashion in all directions. In all directions, save none. That's what I mean by zero-dimensional asymmetry. There is no asymmetry on any one dimension, given a sphere or a dot. Okay, so they all end up having the same field function, the inverse R squared field function. Like the strength, the effect of the field spreads out, gets weaker and weaker at the same rate as a surface area of a sphere grows bigger and bigger in space. That's what I was sort of trying to say last week. Now, what we're going to do in the homework 7 and in my explanation, we're going to move to cases of one-dimensional asymmetry. We're going to move from a point to a line. A line is one-dimensional, but I'm saying more than that. I'm saying a line is one-dimensional asymmetric. So we're going to imagine now like a bunch of net positive charge distributed in a line, like along a wire. Like so the protons, so extra protons are just sitting there all bunched together in a line. And we're ultimately going to ask, what is the field? I mean, the homework ultimately asks, what is the field at some displacement r, perpendicularly from somewhere in this line? Before I go any, so I'm saying this is now one-dimensional symmetry. Specifically, I mean the field lines now, the red. I mean, I'm jumping the gun a little bit in this explanation, but if you look at the red lines in this picture, those are supposed to be the field line. And I'll translate what are the symbols underneath that are sort of getting crowded. The blue symbols underneath, I'll translate in a second. But the red lines are the field lines from this line of charge. What I'm trying to say there is that those lines, that's like a cross section. I'm saying that those lines are spoking out of the charge line. Like they're spoking out in all radial directions. They're like legs from a caterpillar, the field lines are, right? So if you looked at it dead on, if you looked at that whole thing dead on, you would see something like this. If you looked at it edge on, I guess, it would look like what a point is doing. And so the field lines are radiating out in all directions. They are radial, right? They're radiating out in all directions except the axis of the line itself. Again, like spokes from like spokes or like legs from a caterpillar, right? So, right, try to follow this. When I call this thing one-dimensional asymmetry, I'm saying again, like the lines are going anywhere they want the same way in all directions except one. They're not, there's no field lines going parallel to the line of charge. So if you were over here in space and you saw that field line picture, if you were space or whatever, and you see this field line picture, if you didn't see all of these lines bursting out from one point, but rather all of these spokes bursting out from one axis, you would know, oh, there must be a bunch of charge along that axis. The field lines have one-dimensional asymmetry. If you're really following what I'm saying, you'll realize that if I had a cylinder of charge, which is what we eventually get to in the sheet or in this class, like if I then went to a cylinder, a tube of charge, like an actual thick wire, That also would have one-dimensional asymmetry. That also would produce field lines that would spoke out like this. Like what I'm really trying to say, and I will move on. I mean, you either get it or you try, I guess. I mean, I'm really trying to say that that a cylinder is to a line as a sphere is to a point in this respect. I mean, I know that cylinders and spheres are both three-dimensional objects, but hopefully you can see with me that a sphere, even though it's a three-dimensional object, it has zero-dimensional asymmetry. And a cylinder, a rod, is a three-dimensional object, but it has one-dimensional asymmetry. Hopefully, a cylinder's like a blown. Right. Wait, good question. Wait. Oh. Yeah, thank God. I mean, thank God. I'm God is not. Yeah. I'm glad you corrected that because actually I wasn't sure. Yes. So Andy just asked, is my diagram in the line a cross section of the cylinder? Yes, that is manifest. That is definitely a cross section, and it's an important question because, right, like it makes it seem like the lines are all parallel, but they only seem that way because it's a cross section, right? Like if you could draw better, I mean, anybody who can draw better than I can will somehow capture the idea that these red lines are also sort of coming out of the page and they're coming out of the page on a diagonal and out of the page on a diagonal and behind the page they're going at yes. And so the top right corner is a picture of you looking at it dead edge on. So yes, this is just like how a circle is a cross section of a sphere. Absolutely. Yes. Um, so good. So okay. So I think we're on the same page. Well, at least two of us we're on the same page. All right. So all I've said so far in a weird way is lines are to point. No, spheres are to points as cylinders are to lines. That's what I'm trying to say so far. And we're going to now analyze. So I'm really trying to foreshadow, or in case we run out of time at the end, I'm really trying to say that whatever we're now going to analyze the field due to a line of charge. And whatever result we get, well, whatever method we take and whatever result we get should be transferable to the field due to a cylinder. In the homework, you were asked 4 different cylinder cases: conducting cylinder, insulating cylinder, but inside the conducting cylinder or outside the conducting cylinder, inside the insulating cylinder or outside, right? I'm going to walk you through here the basic method, and I'm going to do the hardest one of those for you right before class ends. I'll do the hardest of those 4 cases. But between me showing you the basic method and showing you the hardest case, all the rest of the cases should fall into place, much like they did with the spheres. And I'm not trying to put you in suspense or trick you or anything like that. So to cut to the chase, the field anywhere inside a conducting cylinder, if you're following all the logic from last week, the field anywhere inside a stable conducting cylinder should be 0 for the same reason that the field anywhere inside a conducting sphere should be 0. Like you can prove that to yourself when we do Gauss's law, formally in a second, but that should be the answer for the conductor. And the field outside the conducting cylinder should be the same as the field outside the insulating cylinder. Both of those in turn will be the same as whatever I get for this line. So I'm going to focus on this line. Stop me if you don't understand the logic, but I'm trying to say that I'm repeating the same logic as last week. Once you know a point, then you end up getting what's going on outside a ball, no matter what the ball is made of, because the field lines are the same no matter what the ball is made of. The field lines outside it are the same no matter what the ball is made of. Similarly here, if I can figure out what a field is doing from a line, then I'm going to know what it's doing outside a tube, a cylinder, no matter what the tube is made of. And then the only hard thing is what's it doing inside a tube if it's insulating. So I'll do that next. All right, that's the overview. All right. A couple of pieces of notation. Just like with the sphere insulating last week, we defined rho to be 3-dimensional charge density. We said rho is like dq, d tau, ratio of charge per unit volume. And we declared that it was a constant, at least for the insulator it was. Similarly here, we have a line of charge. We're going to declare that lambda is what we use to designate ratio of charge per length. And we're going to just declare here, I mean, it doesn't always have to be this way in life, but we're saying for this example, assume that lambda is a constant. So the one-dimensional charge density throughout this line is a constant. And we'll assume the total net charge is positive Q. Um, that's what the blue symbols underneath say. Like lambda is defined to be dq dx. And we're saying in this case, lambda equals lambda naught. It's a constant. That's what we're saying. Um, One other thing I want to say about this line. So we're going to, well, I guess it says it on the next page. Yeah, yeah. All right. So here on the next page. Oh, yeah. Here on the next page is a situation again. I just recopied it. We got this long line of charge. We're at some point nearby the line. We want to know what the field is at that point in space as a function of displacement from the line. Oh, why does it say equals zero? It shouldn't say that. Equals, we're trying to solve for it. Um, one, oh, as it says here on the page, one assumption we're making is that the line length itself is far longer, far greater than any distance that we are from the line. Oh, so, what a lot of textbooks or websites will say is that this is an infinite line of charge, or it's functionally infinite or effectively infinite. Now, that doesn't have to be, that's not Smurf Village. Like, that doesn't have to be a fantasy. To say that the line is infinite, really, in experimental terms, in practical terms, means that the line is so long compared to any distance that we are from the line, that whatever meter stick you use to measure the length of the line, if you then went to measure the length that we are from the line, it wouldn't even, that length wouldn't even show up on the meter stick. It would be between the cracks and be zero. We're saying that the distance that we are from the line is negligible compared to the length of the line itself. Why are we saying? And that's totally realistic. That is realistic. That's super possible, because even if this line of charge is like a wire in the lab, even if it's like 50 centimeters long or something, the kind of distances that we're going to be concerned about are distances that electrons would be from the wire, from the line. And, electron distances are preposterously smaller than centimeters. Um, they're like in the negative 20s or whatever. So, well, at least in the negative six. So of meters. So why am I saying? So first of all, it's a realistic assumption that the distance of the line is much, much longer than the distance from the line. Why we're saying that is because we want to ensure that for all intents and purposes, visually, experimentally, measurably, we have no sense of the end of this line. That's the sense in which it's functionally infinite. Like if we were a little electron, some distance from the line, and we're trying to calculate the field at some point near the line, the line's so long that no matter where we go, as far as we're concerned, like we can't see the ends at all. So any funky effects that might be occurring at the ends are not affecting us. Uh, I mean, it's kind of like that we're so small compared to the surface of the earth that whenever we stand on the earth, we don't see, I mean, we don't see the curvature of the earth. It's like that. So these lines, I mean, these field lines might be doing funny things at the ends. They might not have anything to cancel with at the ends, but we don't see that. As far as we're concerned, all the lines are uniformly spoking out. Okay. And we want to know what is the magnitude of one of these sets of lines at some arbitrary point P. What is the E field as a function of R at a small distance compared to the line? That's what we want to know. So we're going to apply the Gauss's law procedure, just like we did last week. Like again, in theory, once you've done one Gauss's law problem, it's always the same method. I mean, just like with Newton's law, you draw a free body diagram, and you divide your forces into components, and then you apply Newton's second law on each axis independently. And it's like, right, no matter how complicated it is, it's the same procedure every time. Same thing here. I mean, obviously, this takes getting used to. That's why we're doing more than one practice problem, but it is the same procedure every time to use Gauss's law to figure out the field. So what is that procedure? Sub-step A, I'm calling them sub-steps because these are all in principle sub-steps of step 4 of the larger, 5-step method. So what is sub-step A? Draw the field lines. Always, whatever your situation is, you draw the field lines first. Okay, but we've done that. Here are our field lines. They're spoking out of the line of charge. They're in red. Okay, so we've done the field lines. Then the most interesting, well, in my mind, the interesting thought step, the step where we really do the physics here, we have to, and it's the same thing we did last week. We have to choose and draw a Gaussian, i.e., closed surface, a surface that literally contains that point P, like a surface at distance r from the charge distribution. That's what we always have to do. We have to choose and draw. This is very abstract. I mean, well, until you get used to it, it can seem abstract, but it's physical. Again, this is like with Galileo's principle of relativity, which is one of the reasons I emphasize it so much. It's like with Galileo's principle of relativity, where you choose a coordinate system before you dive in and start doing computations. And the whole idea there is that your computations will ultimately, the laws of physics will be the same in any coordinate system. You could be in any coordinate system you want. In fact, in principle, you don't even have to know what coordinate system you are in for the laws to be true. But in some coordinate systems, the laws work more easily. I mean, the computations are easier than others. So the effort of physics goes into setting up your situation, considering you're choosing your coordinate system so that your math is as easy as possible. That's really what separates physics from math. In mechanics, in electrostatics, here, very similar thing goes on. The physics that's going to occur, like the law is a law about integrals. The law is this top law on the page that the flux integral, the integral of the electrostatic field through any closed surface is always the same. The flux is going to be the same no matter what surface you choose. So you might say, well, then it doesn't matter what surface. I mean, the law is always true. So it doesn't matter what surface I choose. I'll always get the same flux. That's true. And that's a huge advantage. But flux is not what we want. What we want is field. We want to solve for E. So what we want to do is pick a surface for which the flux integral is so easy to do that we can, in effect, divide both sides by the ds and get the E that we're actually looking for. In other words, I know I said this last week, but we want to choose a surface for which the E is constant in magnitude and direction with respect to the variable of integration, ds. We are trying to choose a surface for which E comes out of the integral so that then we don't even literally have to integrate. Like we are, and we don't have to do any hard integration. If we can get that E to come out of the integral, we'll just literally have E times the integral of ds, which is always just S. That is our goal every time. If we do a Gauss's law problem correctly, we are always taking the E out of the integral and we're never having to do a hard integration. That is the purpose of it. Now, you might even then say, well, if we know that that's going to be true every time, why don't we just skip all the integration and just write E like time surface area, which actually some textbooks. Oh, I'll get you in 1 second. Sorry, great, thank you. Hold on, let me just say this. Like a lot of textbooks and websites kind of skip a bunch of steps and they just say flux means field times area. The reason you don't want to do that, you can't, the reason you have to choose and draw your surface first in order to just like the E is not allowed to come out of the integral unless you know that it does, unless it's constant. And the reason you have to know what surface made it constant is that you have to know what surface area formula you're going to use to divide both sides by to get the E. So I'm gonna pause and say, but so this step is choose and draw a surface. Sorry, I'm totally gonna get Annie 1 second. I'm saying we're gonna choose and draw a closed surface whose surface area we know, like a simple surface, like a sphere or a cylinder or a box or whatever, and for which all the E field lines flow out of that surface always at the same angle and with the same density. That's what we're trying to do right now. But first, unless your hand went down, well, Annie, did you have, or did I just accidentally answer
Uh,
it? Oh,
yeah, no, I ha actually had a question while you were like explaining. Like I did homework 7 like Um, I mean, I submitted today, but I saw the questions and I knew like you probably designed them like intentionally to make like the math work. But I was just thinking like, so basically we have to remove E out of the integral. We have to come up with the diagram that makes all of the arrow like the same property, like they're hitting the surface area, um, like the component of every surface area in parallel with the normal vector of that surface area, and then we take E out, but then the integral still is there, right? And then the ds is still after the integral. So my question is, when we take E out, does the integral and then the derivative basically undo each other so we can just multiply E and S?
Right, exactly. Sorry, yeah, exactly. Like, yes, like 100%. Yeah, what you'll end up getting every time if you do it right is you end up, and I will do it in a second for this, but yes, you get E times S. Like. Let me back up. Integral of ds means S. Yes, just like integral of dx means x. Like, yes, the integral and the derivative sort of undo each other, like you're saying, right? Um, and so in this case, S stands for surface area. So yes, when you take, and I swear to everybody, I'm about to do this, but that's the correct insight, is that E times integral of ds just means E times S, where S stands for the total surface area of the whole shape that you just chose. And so, yes, every single time that will happen, that it's just field times total surface area. But you need to make the choice to know what surface area, like formula from geometry, that you're going to plug in. But yes, wait, does it, yes, does that answer? I think, we'll stop.
Yeah, okay, yeah, I understand. So basically, after like we get rid of the integral, we just like plug in like the surface formula we chose for S.
Exactly. And this is yes. So this is like so many things in physics to everybody. Like, once you get this, it's almost annoyingly simple. Like, once you get what you're doing, and again, I'm gonna do, well, here we go. I'm gonna press on and do it. But like, it's one of these weird things where once you actually, it all looks very like woo, but then once you see what's happening, then you're like, oh, that's all that's happening. And yes, particularly here, but what's happening here is we are trading, we are deliberately thinking in a physical, geometric, maybe abstract way, so that what we don't have to do is a lot of hard computations. Everybody, you may or may not know Gauss, the guy that came up with this, the famous mathematician Friedrich, Karl Gauss, early 19th century mathematician. He is the one who's famous. I'm saying this quickly just to maybe to wake anybody up. This guy, this mathematician slash physicist, is famous for like when he was apparently when he was like in kindergarten or something, he was like bored in math class and he one room schoolhouse, and he's like being all disruptive and all this kind of stuff because I was bored, I guess. And so the teacher tries to punish him and get rid of him and sort of quarantine him and keep him from being distracted. So the teacher, you may have heard this story, the teacher says, will you go to the back of the room and add up all the numbers from 1 to 100 and don't like make a peep or come back to me or bother anybody until you're done adding up all the numbers from 1 to 100. You're like 1 plus 2 plus 3, etc., right? And he's like, whatever. He's like in elementary school, lower. So evidently, according to this story, he goes back to the back of the room. He doesn't, of course, want to do that. He doesn't want to add up all the numbers, 1 plus 2 plus 3. So he thinks to himself, there's got to be a better way. There's like, he's so lazy. He works hard at figuring out a way to get out of the work. So he realizes, supposedly, that addition is commutative. It doesn't matter what order you go in. So he could rearrange it to make it easier on himself. So he thinks 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101, et cetera, and realizes, oh, so it's just 50 pairs, right? It's just 50 pairs of 101. So the answer is 50 times 101, and he does it out, and that's it. Now, No one could prove if that like literally happened as a little child, but he definitely did come up with formulas later that capture that whole recognition about number theory. And the point of the story, I'm not trying to sidetrack, but I'm trying to say it's very illustrative of this man, Gauss, and very illustrative of what ends up happening in physics in general. I want you to know we work hard at coming up with ways to not have to work hard. We are trying to physically picture this so that we don't actually have to do an integral. But you have to understand the integral and the physical picture well enough to do that. To get rid of the integral, you have to get how integrals work. Like for example, the thing that Annie just said, that the integral of ds does mean s. And the integral of e dot ds, well, we could take the e out as long as the e is constant with respect to the ds. So to get to the thing here, sorry. Oh, he is that same guy. Oh, 100%. Oh, Gaussian distribution comes from this guy. This guy Gauss is a monster of mathematics and physics. Oh yeah. And even that, okay, I'm going to sidebar again, but yes, if you've ever heard of any of you have heard of the bell curve, the Gaussian distribution, that's him too. And look, that stuff can get and that's very important, not just in math and statistics, but physics. Believe me, and it can get very heady, all that stuff, Gaussian distribution. But there's also such a basic simplicity to it that everybody in the world that doesn't care about physics or forensic science or whatever, like people in the world know about bell curves, right? People talk about them all the time. Like, oh, that kid is so smart. He's two standard deviations to the right of the center of the bell curve. Maybe they don't exactly say that, but everybody knows about the bell curve because it's so simple and elegant and captures so many nuances with such like a tight package. This is Gauss. I mean, this is the way and then later Einstein saying physicists, I know it all looks very complicated at first, but it's always an attempt. What we're saying is the universe is already complicated. We are actually looking for whatever simplicity we can in the universe. And okay, you get my point. Anyway, so this is an example like that. You will know that you're getting what's going on here when it starts seeming stupid to you. Really, like stupidly self-evident. At first, it seems stupidly irrelevant. Then it'll start seeming stupidly self-evident, and you'll know you're making progress. You, meaning all of you, not just Annie, like any of you. You, you in the back. So here's an example right here. We have to pick and we have to choose and draw a surface, a container, a closed surface at the point P that renders the integral trivial, that brings the e out of the integral, that makes the e constant in magnitude and direction with respect to ds. That all sounds very mathematical, but really all I'm saying in the end is that we have to pick and draw a surface that mimics the asymmetry of the charge itself. That's why I was spending so much time on that at the beginning of this class. It's like it's all really about the simplicity of symmetry or asymmetry. We have a line of charge, so let's draw a cylinder around that line, like because of everything I was saying at the beginning of class. And honestly, if I'm screaming and getting all excited, I just want you to know I did not get that when I was first doing this in college. I remember vividly not being very intimidated by these field lines and by these Gaussian shapes. Like it freaked me out. I'm not trying to freak you out. I'm trying to say it's totally understandable that it all seems like it's out of nowhere. But at some point, but I remember my professor saying things about symmetry that just went right over my head. And what they were trying to say is, look, dude, the line is creating field lines that go everywhere like spokes. If we were to draw a cylinder, we would capture those spokes. And that's what we're going to do. Um, so the yellow in this picture is the Gaussian cylinder. It's in my mind. It's not in the lab. There is a line of charge of protons in the lab, and it's creating field. I mean, I can't see the field, but it's in the lab. But then in order to analyze or compute the field strength at a point like point P, I imagine a cylinder of that radius, of radius R, radius r, to the point P, cross-sectional radius r, and some length, let's call it L. The length of the cylinder will be L. Now here's again where remember the wire is really, really long. The wire is going on in both ends. I can't even see the ends. But in my mind, I just imagine sort of chunking out a representative segment of the line with a cylinder here of radius r. Now I think that's a good shape to pick. Now I go to sub step 3 where I'm going to inspect and verify. I'm looking at the cylinder and I'm considering, do I believe that I've chosen the right shape? Do I believe that I've chosen a shape that will trivialize the integral, that will make the E come out? I always want the E to come out. I don't want to have to actually integrate. Gauss did not want to actually have to integrate. He'd rather think about physics than do the math, so to speak. That's why he's a math genius. Um, so we inspect, we ask ourselves, I mean, this is essentially what Andy was like asking like 5 minutes ago. Like, do I believe that every field line that hits the curvature of the cylinder, do I believe they all hit perpendicular to that curved surface of the cylinder? And yes, I do. They're all like radii of individual discs, so to speak, and they'll all hit the surface the same way that radii of any one disk is perpendicular to any tangent line to the edge of that disk, if that makes sense. Furthermore, I think that the density of the lines is the same on the left part of the cylinder as the right. I mean, the line of charge was uniformly dense. There aren't clumps of charge or anything in it, so there's no reason what the field lines are doing over here should be any stronger than what the field lines are doing over there. So I am somewhat convinced, I am convinced that the lines are hitting the body of the cylinder. Oh, yeah, he is a mathematician. Yeah. The I'm convinced that the field lines are flowing out of the curved surface of the cylinder. I'm convinced that they're all flowing out at the same angle of 90 degrees and with the same density throughout. Like, what is that density? Well, it depends on how many, it depends on my scaling factor. It depends how many lines I've chosen to draw for each Q of charge. But whatever that number is, it's not changing from here to here to here to here to here. Now, okay, a couple of things. I'm saying, this is important. Like I'm saying that a cylinder works as a surface, as a Gaussian surface that trivializes the integral. One way to know whether you follow what I'm saying, because again, this is the weird part, like this part's that I'm on right now, sub step 2. This is really the physics thinking part of it. You can't really skip this part, but so one way to know whether you're understanding what I'm saying is like picture other shapes. Picture if we took this line and we surrounded it or we tried to capture some of it with a sphere like we chose last week or a cubic box. Like picture other shapes in your mind. I mean, start with the sphere, for example. You'll know you get what I'm saying here if you see that if you captured this with a sphere, that would be the wrong shape. Like Gauss's law would still be true. Gauss's law is true for any closed surface we pick. Just like the laws of physics are the same, are true, no matter what coordinate system you pick. But if we were to pick a sphere, even though Gauss's law would be true, it wouldn't be useful. Because if we picked a sphere, can you see that the field line, like one field line would go up through the top of the sphere, I guess, and that would be maybe perpendicular to sort of the top of the sphere. But then the next field line is over here and it goes up and it's hitting somewhere to the left of the top of the sphere. It's hitting a part of the surface that is like now at an angle, but the line is going straight up. Do you see what I'm saying? Right. And then more and more extreme as you go over, the lines keep being straight up, but the surface of the sphere is like sloping down. So they would not hit the sphere all at the same angle. And by that reason, too, if you start looking at them, they would start relative to the sphere. They would get like more and more dense over here at the edge of the sphere than at the top, because over here at the edge, there's less sphere area, but there's because it's like shorter, but there's just the same number of lines. I so I'm trying to say when I say that all the lines hit the cylinder in the right way, you can really know that you believe me or you're satisfied by that if you consider an object for which they would hit it in the wrong way. Um, and so you may want to stop. So I'm saying cylinder good when we're surrounding a line. The E field is constant with respect to ds. It would not be, if we drew a cube or a sphere, Gauss's law would be true, but we wouldn't be able to take the E out of the integral. So we really, or at least I couldn't do the integral. Or if I could, if I could write a whole computer code or something to like numerically do the integral or something, then I maybe I could do that. But then I might as well have just integrated Coulomb's law. Then Gauss's law is giving me no advantage. But okay, so I draw a cylinder. So now I go to substep 4. Since we have verified, well, largely, since we have largely verified, we could move on to substep 4. Except there's one thing. If you're really following me, you, um, the field lines are supposed to hit the surface of the Gaussian shape, they're supposed to hit the same way everywhere. And everything I just said was about the girth of the cylinder. If you're really following me, you at some point it might have crossed your mind, like, but wait a second, what about the caps? Are the field lines hitting the caps of the cylinder perpendicular to the caps? And that's a very good question. That is worth thinking about for a minute. So it's like anything. So if it crossed your mind, you're not crazy. But there is a response. Um, Again, remember the line of charge, the thing that's actually in the lab that we're analyzing, the line of charge is going on forever, essentially. This cylinder is just chopping off some representative segment of it or enclosing some representative segment of it. The cylinder, in other words, does have ends. It has to because it's a closed surface. It's supposed to enclose a defined amount of charge. So there are caps to this cylinder. What's going on in the caps? Well, my answer is here in white. My answer is that the field lines are perfectly parallel to the caps. So indeed, the angle is not 90 degrees anymore, but it's so not 90 degrees that it's 0 degrees. The angle between the field lines and the surface. The angle is so, now if the angle had changed from 90 to 89 or something, oh, then we'd have an issue. We'd have to deal with cosine, and then we couldn't take the E out of the integral, but that's not what happened. When you get to the caps, the angle changed from 90 degrees to 0 degrees. Well, technically from 0 to 90, you got what I'm saying. Like they're parallel now. So that means in the caps, there's 0 flux. Flux means some kind of component of field line that's perpendicular to the surface itself, or like the way Annie put it before, which is more correct, really. For there to be flux, there has to be some component of the field line that is parallel to the norm of the surface. Well, out here, there is not that at all. The field lines are fully flush with the caps. So what does that mean? Does that throw off our whole game? No, it just means that the caps contribute 0 to the whole integral. So they neither throw us to the left nor to the right. They don't bother us at all. Remember, an integral is a sum. The total flux integral of something is the flux plus the flux plus the flux plus the flux, however you want to do it, right? It's a sum. So if two pieces of something have fluxes of 0, they're just not changing the whole rest of the remaining flux, honestly. So it's worth thinking about the caps, but they're not going to throw us off. They're just going to contribute nothing to our analysis. Okay, but that is 100% because we're approximating that this line is really long. If the line were too short, we couldn't say that, and things would get thrown off. So that's why we're dealing with a very long line here, where the field lines are all the same. Okay. So we can now go to substep 4. We write down Gauss's law, like we got it. Just like with Newton's laws. With force problems, you always, after you draw the free body diagram, you write down Newton's second law independently along each axis, and then you start expanding the left side to get the acceleration, right? Same deal here. We write down the law. The total flux through any closed surface is equal to the charge enclosed by that surface divided by a constant. Okay, so I wrote it down. So now substep 5, the final substep, we're going to expand and solve essentially. But how do we expand and solve? We do the thing that some of you put in the chat and then Annie put in the not chat, or I mean, some of you put in the private chat and then Annie put in the public chat. We're going to trivialize that integral. We're going to take the E out of the integral because we can, because we choose the surface that allows us to, right? And then we're going to say, oh, okay, E times the integral of ds is E times S. And S means total surface area. Um, and that means total surface area of the shape, like that means total surface area of the closed surface through which the flux is occurring. It means always the total surface area of the surface that we chose. So this is the moment where you can't cheat. Like, and again, I'm emphasizing this because I know from experience that all over the web and in books and stuff like that, it will say things like flux equals field times area or field times surface area, like which is what I'm saying here. It will just say that. And it'll make it seem like you don't have to go through all this work and you don't have to do the integral and then trivialize. Like it'll just get to that final result often in certain websites and things like certain websites and things like that. But I'm not making an ethical point here. I'm making a practical point that if you skip all the steps that I just said, if you try to end run the physics and just go to memorize that flux equals field times surface area, you don't know what surface area to put in. What ends up happening to people that don't get this is they just always end up putting in the surface area of a sphere because that was the first example they ever did or something. But it's not, okay? It's the surface area of the shape that you chose. So you got to choose a shape. So we chose a cylinder. So the surface area of a cylinder is a cylinder of radius, cross-sectional radius r and length L. The surface area of a cylinder is 2 pi RL. Did I memorize that? I mean, I guess I did accidentally by this point in my life, but it's really not a memorizer, right? I mean, I hope you can understand it. The surface area of a cylinder is like the circumference of the top of the cylinder, 2 pi r, times the whole length of the whole thing, right? It's like, what is a cylinder? It's a stack of rings, right? You see that? So it's 2 pi r times L. And notice it has two invocations of length in it. Like it has R is measured in meters and L is measured in meters. There's two levels of meters. There's meters squared because we're talking about area, right? I don't think that I'm just trying to emphasize it may seem for some people at this point in the course, it seems like suddenly there's a million geometry formulas that they never knew that they were going to have to know for physics. And it seems like unfair or annoying. And maybe it is annoying, maybe it is even unfair. But I'm trying to emphasize what happened to me, at least, is when I first learned geometry, yeah, there were all these formulas that I just had to memorize. But by the time they started meaning something in physics, I started seeing that most of them were not memorizers. They just made sense. Not just made sense, but they make sense. And if you're asking, why do we have to care so much about geometry? Because what we're really studying now is the nature of space, which is called geometry. So the surface area of a sphere is 2 pi RL. Therefore, the left side of Gauss's law is E times, it's not really a dot product anymore. It's like just literally times 2, 2 pi RL. So that will equal the charge enclosed divided by that constant, right? Only question is what's the charge enclosed? Now remember, so I'm on the right side of the thing now. The original line of charge was identified by its density, lambda. That's the amount of charge per unit length. That's what was a constant throughout it. Now, I happen to have said that the whole line of charge had a total charge of plus Q or something. I mean, I said that, that's true. But again, be advised, like, we're not enclosing all of the charge of this line. I mean, it's a really long line. We just have we can't see the ends, so we can't put a closed surface around the ends. We have this closed surface over like a midsection or representative segment of this line. So we're not enclosing all of the original Q. I don't know offhand how much charge we're enclosing. What I know is the same thing I knew last week when we looked at spheres. I know the density of the charge is a constant. dq dx is lambda naught. So I know, in other words, I know, let's make this a little more explicit. I know that the charge enclosed per the length we look at is equal to the total charge per the total length, whatever that is. But that ratio is called lambda, right? So charge enclosed, maybe I just made this harder than it is, but I'm saying charge enclosed, I'm saying charge enclosed equals lambda times the length of the cylinder that we drew, right? That's L is not some given in the problem, but L is the length of the cylinder we drew. Whatever that length is times the charge per length, the charge density, that's the charge that we enclosed. So E times 2 pi r L equals lambda times L over epsilon naught. Notice two things now. First of all, this is what ends up always, if you've done things correctly in a Gauss's law problem, on the left side, you'll always have E times some sort of known surface. I mean, yeah, some type of known surface area formula written out. And on the right side, you'll have some expression of constants, of constants. So in the next step, always what we're just doing is dividing both sides by the surface area to get E. That's always what we're doing. Again, we have to go through all this rigmarole in order to know what the surface area is that we're dividing both sides by. That's number one. But number two, frequently, as you see here, frequently there's sort of some dummy variable in there. There's some kind of dimension or description of the Gaussian shape that we made up in our minds. Like in this case, L. In this case, we made up a shape of length L. Now, and that's to use it to compute something. L wasn't a given in the original problem. L doesn't describe anything in reality. L is just like a dimension in our head. We can use it to make our life simple, but it has to, if this whole thing is going to be an answer that means anything, then at the end of the day, that L or that dummy variable or whatever we made up has to cancel out. It can't still be in our answer because it wasn't a measured constant in the problem. I hope that makes sense. So, but that's what happens. So in other words, just like last week, something canceled out. I don't even remember what it was, but here the L's cancel out. And so we get as our final answer, with plenty of time left, strangely. There's one more thing we have to do, but we won't have to rush it as much. We get as our final, so please do ask questions if you have any. We are on track. And again, sidebar, I am behind with your work and I am not happy about that, or I'm happy with, yeah. And some of you might be behind work that you want to give to me. So we're both giving each other a chance with that. But just so you know, with the curriculum, we're not behind. Like we're definitely getting to everything that we need to get to if you care. You might care because we get to some pretty interesting punchlines at the end of this course when we get to the end of the course. So anyway, um, I'm saying that the answer to this problem is uh is what's boxed at the bottom of the sheet. I'm saying like we got E field is a vector function. It always has direction. The direction is donated is denoted by the unit vector R. So we'll get, what is that? I know that's still sort of confusing to some people. That R unit vector is just saying that's the direction from the center of the charge to wherever the field point is, right? So that R, what it means in English is that the direction of this field, wherever we are looking, point P, the direction of the field is pointing radially out, which we knew, I mean, from our picture. I mean, that's how I know from our picture that the direction of the field is radially out. The magnitude of the field function is what we've just gotten here. That's interesting. That was really the goal of all the computation and really is an interesting result. What we're getting here is that the field magnitude at a point R from a line is 1 over 2 pi epsilon naught, like a constant, times lambda, the charge density of the line, divided by R itself. Notice this looks very similar to the field function from a point like this looks, or a sphere. This looks very much like Coulomb's law, except not. I mean, it looks very much, but there's one small difference and then one fundamental difference. I'm going to turn the page and make the compare and contrast. But before I even make that, like, please note, lambda might be sort of intimidating you, but lambda is charge density. Lambda is like how we best describe the charge once you have a one-dimensional region like a line. If we have a ball, we describe it with rho. If we have a sheet or something, we describe it with sigma. Like, it's just like saying Q. What I'm just trying to express is that that numerator there is just like saying Q, only it's the way we say it once we have a shape like this. Okay, so this really has the format of Coulomb's law, like strange constant, charge in the numerator, then divided by some power of R. Very much like it. The so let's directly compare and contrast. Yeah, compare the point to the line. If you have 0 degree asymmetry, right, like point or sphere, like I was saying at the beginning of class, like the results from last week, you get a function that exactly like Coulomb's law. You get the inverse R squared function, right? 1 over 4 pi epsilon naught, Q over R2, R hat. Once you have a line, one-dimensional symmetry, then, okay, first of all, the constant changes slightly. Not really. I mean, the constant is still that funny combination of pi's and epsilon naught, like it still has all the same units and everything. It's just, it's off by a factor of 2. Yes. Why? Well, because the surface area of a sphere is 4 pi r squared, and the surface area of a cylinder is 2 pi r so squared. I mean, is that what I meant to say? Or 2 pi r L. So like, yes, the constant's off by a factor of 2, but that's not a big deal. That's just a number. That's not conceptually different. Um, but what's different is that the power of R in the denominator. Notice that for 0 dimensional asymmetry, the field function is directly proportional to R to the -2. If we go up one dimension of symmetry, apparently the R dependence goes up one power to R to the -1. Interesting. And not, I mean, and this will always be true. This is like a result or a finding. To be a little bit more expansive about it, well, yeah, okay. So here's the observation. As we increase the degree of asymmetry, the degree of R dependence, we also increase that. Now, increase is a funny word. I mean, it's going from 2 to 1, but technically it's -2. So you could say it however you want to say it. But I'm saying when the asymmetry went up from 0 to 1 dimension, the R dependence changed from R to the -2 to R to the -1. So if you follow what I'm saying, then you'll see that whatever I just concluded about lines must be true about cylinders. The field line picture for a cylinder is the same as the field line picture for a line, just like the field line picture diagram for a sphere is the same as for a point. So whatever if you follow what I just did as the answer for the line, I'm telling you straight up, as far as homework 7, or maybe if something's on the final exam or something, I'm telling you straight up that the field outside some cylinder had better be this same answer. Like, do it still, do out the Gauss's law. You'll do the logic, but you'll see the field lines are the same. You're going to pick a cylinder again, just like here. And if you're outside the cylinder, you're going to enclose the same amount of charge as you did if you were outside a line. Like, you're going to enclose all of the charge in that region. So whether it's conducting or insulating, if you're outside the cylinder, you'll get this function, lambda over R. If you're inside a conducting cylinder, you'll get 0. So that's 3 out of 4 of the cylinder cases. We have 6 minutes. I'm going to do the last one. But also notice, because I think the homework then goes on to ask you about a plate. I mean, it all seems very intimidating, and abstract, but it's just going in levels of symmetry. It then goes to a plate, a sheet of charge. That's 2-dimensional asymmetry. You got an x-axis and a y-axis now. The field lines are just going to come straight out of the plate, up and down. Like, they're not going to radiate out. They're not going to spoke out. They're just going to slam out because they're now asymmetric on 2 axes. They're only symmetric now on 1. So they'll go, right? So if you do the Gauss's law argument procedure we've been doing, you're going to find a checkpoint. You'll know you've done it right with the sheet if you get that the field depends on R to the 0, which means not on R at all. It means dependent on the number 1. which means you'll get a constant field. You'll know you've done it right. If you get a field expression, I'm not saying no number at all or no, but you won't have an R in your answer if you do the plate correctly by the same procedure. Okay, that's two. But finally, the one example I want to do for you with 5 minutes left is the heart of the cylinders. I'm telling you that if you follow the line that I just did, that gives you 3 out of the 4 cylinder cases straight up. But the hard one is, what if you're inside an insulator? Just like that was the hard one with the sphere last week. What if the charge is uniformly distributed, plum pudding, throughout the volume of a cylinder? So rho equals rho constant. Now I'm going to do this fast, but I'm going to do it. It's the same procedure. If you want to know the field at a point inside an insulating cylinder for which the charge density is a constant, the three-dimensional charge, what's the procedure? The procedure is first draw the field lines. There they are in red, same as before, spokes. Because again, we still have the same symmetry. So you draw the field lines. Then you choose and draw a Gaussian surface that will render the integral trivial. So what are we going to choose and draw? Again, a cylinder. Only thing is now we're going to draw the cylinder inside. So the yellow thing is our Gaussian shape. It's in our minds. Inside that blue cylinder that is the real thing in the lab, like some thick wire. So we draw a Gaussian cylinder inside that thick wire. Then step 3, inspect and verify. I'm inspecting and verifying. It works just like it did before. So then step 4, write down the law. Step 5, expand, well, trivialize the integral and expand both sides. Okay, I trivialize the integral because it works just like before, same field lines. So I write E times 2 pi RL, again, just like before. And the right side is Q enclosed over E. So the only question now is, what's Q enclosed? Okay. You invoke the same concept as I invoked before and before. I don't know the Q enclosed. I don't know how much, like I'm somewhere inside this tube. I'm not enclosing all of the charge, but I know the density is a constant. So I know the density is a constant. So I know charge per volume has to equal charge per volume anywhere. So the charge enclosed per volume enclosed has to equal the total charge per the total volume. Volume of what? Volume of a cylinder. What's the volume of a cylinder? It's the area of a disk times L, right? Like the surface area of a cylinder is a bunch of rings stacked up. The volume of a cylinder is a bunch of disks stacked up, like for reals, yo, right? So the volume of a cylinder is pi r squared L. Notice three, like r squared times L. That's 3 dimensions of length. It's going to be in cubic centimeters or whatever, as it should, because it's volume. Do you see what I'm saying? I mean, I'm going for, you see, okay, 2 minutes left. So the pi's cancel and the L's cancel. So the charge enclosed is some ratio of the total charge. What's the ratio? The ratio of the r squareds. Just like the ratio of the charge enclosed for a sphere was the ratio of the r cubed. Same idea, but now we're, okay, same idea. And because L, no matter where you are, the L is the same. Anyway, so we plug in both sides. E times 2 pi RL equals Q r squared over capital R squared. The lower R, the lower case R's cancel out. L doesn't seem to cancel out, but Q over L is what we mean by lambda. So what we get at the end of the day, just once we do the algebra, we have 2 minutes, we have a minute and a half left. At the end of the day, we get that constant, okay, times lambda. There's no reason sorry. Times lambda in the top, as you'd expect. And we have a weird constant at the bottom, but we have r, lowercase r, in the top. This is like, please note, this is just like the insulating sphere, in that, again, this, when you're inside the thing, walking out from the center, getting farther and farther from the center, the field gets stronger and stronger. Hang on one second. And I'm going to ask you to wait after, like, I will totally answer your question, but let me just let everybody else go. Sorry. I'm saying that the field will get stronger and stronger as you walk out from the center, because you're in effect standing on a larger and larger tube of charge, like just like in the ball from last week. As you get farther and farther from the center, the field gets stronger and stronger linearly. So that's it. That's the answer to the hardest one from homework 7. we're done. Thank you for being so patient. Thank you for being patient in general. We're done. I mean, Annie, I mean, anybody who wants to hear Annie's question, whatever, you're welcome to stay. I'm going to answer, or any other questions there are. But I'm just saying you can go, and I'm turning off the recording. So bear with me for a second, but I'm not going anywhere, I promise.